Alright, so today we're going to be talking about derivatives. So what exactly is a derivative? A derivative is the rate of change of a function during an infinitesimally small period of change. So we know that the rate of change of a function over a period, let's say it's from x to a, right? We can write that as f of x plus a minus f of x all over a, as that's the period of change. Sorry, this should be x plus a. And so if we want a to be an infinitesimally small number, which is what the derivative entails, we can write the derivative, or f prime of x, as, let me write this in a different color, this in red, as the limit as h, we'll use h, approaches 0 of f of x plus h minus f of x all over h. Now, given this definition, let's just try this for a random function. Let's say f of x equals x squared. So we know that the derivative can be written as the limit as h approaches 0 of x plus h squared minus x squared over h. And by distributing, we get the numerator to be x squared plus 2xh plus h squared minus x squared all over h. These x squareds cancel out, and so does this h and these h's. And so we're left with the derivative equaling the limit as h approaches 0 of 2x plus h. And since h is 0, this just equals 2x, which is our derivative. Now, let's use this information. Let's actually prove the power rule, which is going to be one of the main rules, per se, of derivatives that you're going to use for any polynomial that's in the term x to the n. And it states that any polynomial in the form x to the n, that the derivative, or dy dx of x to the n, equals n times x to the n minus 1. And we know that this holds true for x squared, as its derivative is 2x, right? But let's see how this works for any polynomial in the term x to the n. So to our right, I actually have the Pascal's triangle, as it's going to make it a little bit easier. And so let's just write the derivative of a general x to the n term. And that'll be the limit as h approaches 0 of x plus h to the n minus x to the n all over h. And so in the Pascal's triangle, we know that these terms, or all of these terms, are going to be your x to the n terms, right? This is going to be x to the n term. These are going to be your x to the n minus 1 terms. These your x to the n minus 2. These your x to the n minus 3, and so on. And this triangle will go on forever, obviously. But now that we know this, we saw that in the previous one, or in the limit we took from x squared, that this term, this x to the n term, doesn't matter because it's going to be canceled out by this x to the n term. And all these other terms are going to have an h term that's greater to the first power. This will have an h squared, h cubed, and so on. So we can actually generalize this, and we can say that this is approximately this 1, 2, 3, 4, or actually just n times x to the n minus 1. And that is the most basic proof of the power rule. Obviously, you can go deeper, but this is what I got so far. And let's talk about some special derivatives, or derivatives that you should know, right? And that's going to be the derivative of e to the x, the derivative of the natural log of x, and the derivative of sine of x. You don't actually need to stick around for this, but if you are interested, I will be proving these using the limit definition. So the limit definition states that the limit as h approaches 0 of e to the x plus h minus e to the x all over h is the derivative, right? And so now that we know this, we can set this up to equal e to the h minus 1 times e to the x all over h. And we're going to try to rewrite e to the h minus 1 and h as to isolate this e to the x term, which is actually going to be our final derivative. And so to do this, I'll choose a new color. Let's choose blue. I'll set a derivative, not a derivative, a variable, let's say y, equal to e to the h minus 1. And then h equals the natural log of y plus 1. And now we can rewrite this limit, right? We can rewrite this limit as the limit as h approaches 0 of y times e to the x. Or actually, I'll write this a different way. It'll be e to the x over 1 over y times the natural log of 1 plus y. And so this can be written as e to the x over the natural log of 1 plus y to the 1 over y. And we know that the number e, or Euler's number, is equal to 1 plus 1 over x to the x. And so that we can substitute this in to be e as y, let's just say, equals 1 over x. And if that is true, we can say that, I'll change colors again actually, sorry for the lack of space, the limit as h approaches 0 of e to the x over ln e equals e to the x, and that will be our derivative. Now let's try proving the natural log of x. We have the limit as h approaches 0 of the natural log of x plus h minus ln x all over h equals, and we can set this natural log, or sorry, this expression, we can combine these two terms using our logarithmic identities to be the natural log of 1 plus h over x, as we just make that equal to x plus h over x. And I'll just write this 1 over h out here. And the reason for this is we can actually rewrite this limit as the limit as h approaches 0 of the natural log 1 plus h over x to the 1 over h. And as we just asserted, actually, is that we just asserted that the definition of e is 1 plus 1 over h to the h, right? And if that's true, right, if e equals 1 plus, let's just say h to the 1 over h, right, this is going to be, this term is going to be the limit as h approaches 0 of e to the 1 over x, as given by this term, and that is just the same as 1 over x, which is our derivative. And finally, let's prove the derivative of sine of x. That's actually going to be cosine of x, and the opposite is true, but it still be negative. And to prove this, we're going to use the limit definition once again, the limit as h approaches 0 of sine of x plus h minus sine of x all over h. We can use our addition subtraction properties for sine, say that this is equal to the limit as h approaches 0 of sine x cosine h plus cosine x sine h minus sine x over h. We know that cosine h equals 1, and sine x minus sine x is going to be 0. And we'll be left with this, the limit as h approaches 0 of cosine x times sine h over h. We know that the limit as h approaches 0 of sine h over h equals 1. So we can take that out, and we're left with the limit as h approaches 0 of cosine x, which is just cosine x, or our derivative. All right, thanks for watching.